In the lesson today, we're going to start investigating probability. So in the previous lessons, we've been looking at how we can describe data sets, and now we're going to move into the language of statistics, which we discussed was covered by probability. And so for the next few lessons, we'll be looking at sort of the foundations of probability, how we can answer questions with probability, and then once we have that whole tool set for ourselves, we'll move back to doing sort of more statistics at that point. In today's lesson specifically, we're going to be introducing the concepts of sample spaces and of events. And so sample spaces and events sort of form the foundation for thinking about probability, at least at an introductory level. And so these are sort of core concepts that we'll be using as we go throughout the probability in this course. In terms of learning objectives for today, we want to be able to define what probabilities actually are formally in terms of our sample spaces and events. And so we'll introduce what all of these words mean in due time. We also want to understand sort of the basic properties or the basic operations that we can take on events, right? And so this is going to be using some set theory. And so doing that, we want to sort of understand how we can mathematically manipulate these ideas. And so to begin, I just want to sort of address at a high level, what are the types of things that we can think about with probability and sort of get a sense of how we abstract away the specifics to do math with these concepts. And so sort of there's several areas that you might experience probability in your day-to-day life. The maybe most common example is if you're looking at the weather forecast, right? We talk about the probabilities that certain forecast patterns come up. If you've ever been hospitalized or you have someone in your family who's been hospitalized, there's a lot of probabilities associated with medical treatments or with medicine. During the pandemic, we would have seen lots of probability discussion about the efficacy of certain treatments for COVID, right? And of course, if you're used to playing games, right, rolling dice, we talk about the probabilities associated there. And so we have this idea that probability can map onto all of these different topics, right? And quite varied topics. And so the idea is that we want to sort of set up a mathematical framework that can capture these notions of probability, regardless of whether we're talking about the weather or medicine or games of chance or sort of anything else. And so we'll grab different examples from sort of all over the place. But again, the idea with what we're trying to do here by defining events and sample spaces is to be able to take any specific scenario, abstract that away to sort of the core math that's underlying it, and then use the tools of probability to be able to answer the questions that we might care about. At a high level, probability is the study of uncertainty or of randomness. And we've discussed that uncertainty is central to the study of statistics. So the idea with probability is that we're trying to understand how can we make sense of uncertainty? How can we quantify it? How can we sort of learn to make decisions when we are faced with uncertainty, right? And so probability is the way that we quantify this uncertainty. We briefly touched on statistical experiments in the past, but in statistics, we refer to an experiment as any action that has an uncertain outcome, right? We can think about sort of endless numbers of examples of statistical experiments. So if you think tossing a coin or rolling a die, right? You can also think about something that may seem less like a statistical experiment at first. So if we're weighing the material that's produced in sort of a manufacturing process, right? We don't know exactly how much is going to be produced there. And so because of that uncertainty, it's a statistical experiment, right? We talked about giving a medical treatment. We could think about observing the weather. So anytime that there's a process or population where the observation that you're going to make has an uncertain outcome before you've made it, we can think about that as being a statistical experiment. Now, when we're talking about the sample space for an experiment, this is going to be the collection of all possible outcomes that we could possibly observe. Right, so if you think about flipping a coin, the sample space on a single flip of the coin is going to be a heads or a tails, right? But if you think about flipping a coin twice in a row, now suddenly we're going to be thinking about the ordering of all possible sequences, right? So heads, 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 tails, tails, heads, or tails, tails, and so on. If we're thinking about something that's a little bit more complex, so say observing the weather, we'd have to define what we actually think the sample space is going to be, right? So there's going to be some range of temperatures that we could possibly observe, or some set of precipitation patterns, or all of these different things. But any sort of possible outcome has to be included in our sample space. And then the idea with an experiment is that we're going to be observing some sort of event that's coming from our sample space. We denote the sample space with this script S, right? So the script S refers to the set of all possible items. And as I was just mentioning, an event is any specified collection of outcomes from within the experiment, right? So this could be a simple outcome, right? If you're flipping a coin once, we could say that an event is you get a heads, right? But you can also think about events as being sort of multiple different possible outcomes. So if you're going to be rolling a die and you say an event could be that you roll an even number, right? That's actually the 2, 4, or 6 coming up on a die, but we can still call that an event. So it's a collection of outcomes from an experiment. In terms of mathematics, we think about events as being subsets of our sample space, right? So again, we're trying to do all of this to sort of abstract away any specific notions that we might have. And so to clarify where we're at, the sample space is going to be a set S, and it's going to be the set of everything that we could observe from our experiment. And anything that's a subset of that is going to be considered an event. In terms of the language that we're going to use, if we've conducted an experiment and a particular outcome has occurred, if that outcome is part of the event, then we say that the event occurred, right? And so in the example of rolling a die, if the event that we care about is an even number comes up, then if we roll a 2, we say that the event occurred, right? And so that's just the language that I'll probably be using throughout the lectures here. So we have different properties or operations that we can think about on events. And I'll just remind you again, events are just sets of different objects, right? And so let's say that we have A and B, and both A and B are events of interest, right? So we're sets, they're elements of our sample space. We can talk about the complement of an event, right? And so we denote that with a C above it, right? C for complement. There's other notations that you might see used, but in this course, I'll try to stick to using the specific complement notation. And the complement of an event is the event that the event of interest does not occur, right? So a complement is the event that A does not occur. So if you think about A being the event that an even number is rolled, then a complement would be the event that an even number is not rolled, or in other words, that an odd number is rolled. Right? And so the complement of an event is everything that's in our sample space that's not in the original event. We also can think about the union of two events, right? So if we have two events A and B, and we denote the union with sort of this cup notation here, right? So we'd read that as A union B, and that's the set of all outcomes that are in A or B or in both of them, right? And so if we wanted to say that A was the event that an even number is rolled, and B is the event that a number less than or equal to 3 is rolled, right? Then A union B is going to be the event that either an even number is rolled, or that a number less than or equal to 3 is rolled, or both, right? And so if we think about what numbers would clarify or classify there, we would get 1, 2, and 3 from event B, and then we would get 2, 4, and 6 from event A. Now, 2 is in both of those, and so it's still included in this set here, right? And so in total, we would see 1, 2, 3, 4, or 6. And so if we think about A union B in this case, it's everything except for a 5, right? And so then if we think about the complement, if I had said the event that we roll a 5 is our event of interest, the complement of that event is the same thing as A union B in this other event, right? And so you can start to see how using different events, we can begin to construct up sort of complex outcomes or represent different outcomes in different possible ways. In addition to the union, we also can see the intersection, right? So it's denoted with this sort of upside down U. And A intersect B is the set of all outcomes that are in both of them, right? And so in the event of A and B that we had just defined there, the intersection of those is going to be the number 2, because the number 2 is the only event that is both less than 3 and also is even, right? And so the intersection, they have to be in both. The union, they're in either or both. Now, if we say that the A intersect B is the empty set, right? And so we denote the empty set as this sort of item over here that looks a little bit like a 0. And so if there's no elements that are common between the events A and B, then we say that they're mutually exclusive or that they are disjoint. They mean the same thing. And so, for example, we could have the event less than or equal to 3 or the event greater than 3, right? And if you try to take the intersection there, there's no number that is going to be both less than or equal to 3 and also larger than 3. And so that's empty, and we say that those are mutually exclusive events. One really useful tool to start thinking about sample spaces and events is to use Venn diagrams. And so I'll just pull open the whiteboard here and sort of discuss what we're looking at, right? But with a Venn diagram, the idea is that we draw a rectangle, and the rectangle here is going to represent our sample space, right? So I can label that as our sample space. And then within the rectangle, we can think about drawing different areas that represent different events of interest, right? So we might have some event here, it's the event A maybe, and we might have some event here, which would be the event B, right? And so we can think about, say, labeling this as B, labeling this as A, right? And then we could think about what are the different areas that we might care about, right? So if we think about what is A complement, well, A complement is going to be everything that's not in A, right? And so we'll have all of this area outside of our sample space here that's not in A or B, right? But we're also going to have this whole area of B here, which is not going to be within the event A. But we won't include that overlapping area between A and B right here, right? So that would be the complement of A. We could also think about doing, say, A union B. And the idea with A union B is that we want everything that's in A, we want everything that's in B, and everything that's in both of them, right? So it's just that whole area that we'd be shading there, right? If we think about the intersection, A intersect B, right? That's going to be just this area here between the two sets A and B, right? And then you could think about using this to try to draw out sort of more complicated areas, right? And so if you wanted to say take A intersect B and then complement that whole set, well, now it's going to be everything that's not in this little box here. And so that would be everything that's in A but not B, everything in B, not A, and then also everything that's outside of here, right? And so the Venn diagrams become quite useful for playing around with different sets here. One last thing that we can include on the diagram here is if I draw a set over here, which is, say, the set C, then we could say that C and A, so A intersect C is going to be the empty set, right? Because they don't overlap. Same thing with B intersect C. It's going to be the empty set because they're not overlapping. And so then with that, we can see sort of disjoint sets. Now, of course, if we drew in, say, an additional event over here, we could put that right there, right, and call this one D. Well, now D and B intersect, but D is disjoint with A, right? And so A and B intersect, B and A, as well as B and D intersect, and C is disjoint from everything else, right? So they just become this useful way for visualizing the different events. If you're working within a sample space that's sort of well-defined, you can start to label these events here more specifically. But overall, it's a useful tool to start reasoning about what is the actual space that we're thinking of. In summary, with probability, what we're looking to do is study randomness or uncertainty. A statistical experiment is any action where we don't know for certain what the event or what the outcome is going to be. A sample space is a set that contains all of the possible outcomes from an experiment. An event is any subset of the sample space. And then we could include sort of the basic operations or the basic properties of events, which we could see as taking complements, taking intersections, or taking unions. So in the next lessons, we're going to start using some of this to actually start working within probability. And I'll see you all in those lessons.